Yeah, hi, I'm excited to be here, and my talk is about data preparation. Just to give you a bit more background about myself, I'm at Trifecta, and this is a startup that was founded about 4.5 years ago in San Francisco, focusing on data prep, and I joined as one of their first employees about 3.5 years ago, shortly after my PhD. To start out with, I want to show you a couple of exciting applications of data science where it really shows that data science can revolutionize industries. And the first one is Royce. So Royce used to produce cars, but this has changed. Now, what they produce are jet engines, and the product itself is not even the only part of what's so important about them. Even as important is data science. So each jet engine has literally hundreds of sensors, and Rolls-Royce is not selling jet engines; they are renting them. That way, during the lifetime of the jet engine, they can constantly record and monitor all the data from the sensors. And the impact of that is that they apply data science to improve the maintenance schedule, to improve the lifetime of such a jet engine, to max out the performance, to save fuel, and various kinds of other things. So now it's essentially jet engine as a service, where they use data science to kind of like improve various aspects of the service and also improve their revenue. Obviously, they are also applying data science in other pieces, and just to give you an idea of the amount of information that's being produced, you see all those little blades inside the jet engine. During the manufacturing process of each blade, they record 0.5 terabyte of data that they can then analyze and use that to improve their manufacturing process. So this is an example from industry. But obviously there are other parts where this is really important, and one of our customers is the Royal Bank of Scotland. So in finance, they're using data science and especially integrating many different data sources. The project that they've done with Trifecta integrates transaction data, account changes, calls that you make to customer support, web chat logs to customer support, in order to create a holistic image of and model of what people ask for when they ask customer support. So with this holistic 360, they can then create models that they can give to their, or build into the tools that their service representatives have. So when you ask somebody from RBS on web chat, or you give them a call, they have a much better idea of what you might want to know, of what service you might require, based on machine learning, based on the integration of many different pieces of data to create those models. And it's not just limited to business. Data science is becoming very prevalent. Another big example is the US elections, coming up again in a new edition shortly. The data from the last elections was that Barack Obama raised over $1 billion of funding. And data science played a huge role in that. So what they do is they take information from pollsters, they take information from previous fundraisers, from their field workers, from voter databases, from consumer databases, from social media, from their own voter files. They take all this data together, even consumer data, to create models. And these models are used for the obvious things, to predict voter turnout, to predict the outcomes in certain districts, but also to help with fundraising. If you know kind of like who's most likely to give you money, Obama was supported by a lot of small donors, so they had a really good model, so they knew who to ask and for how much. So they could aggregate a lot of money. With that money, they could buy TV ads. Obviously, they use data science to choose which TV ads to buy on which channel, in which region, and when they should air. And also to persuade voters to vote. Oftentimes, voters don't show up at election day. So an important piece of any election campaign is to make sure that the voters, for whom you know that they will vote for you, actually show up and vote. So for that, they used all those different data sources that I mentioned to create models again, to have ranked lists of voters, ranked by persuasion probability. So how likely is it that we're able to persuade them to actually show up on election day? The outcome was really impressive. I mean, you remember Obama winning the elections, and now there are actually businesses helping with that. So one of our customers, Nation Builder, their business model is to create a national voter file. So they get all the voter registration files from all the 50 states. Those happen to be in very different formats, so there's a lot of data preparation going on. And they put those together into the data product, enrich them with additional data, and sell that to the Republicans, to the Democrats, and to businesses that are interested. So this just shows how prevalent data science is, and it might lead you to believe that data science has died. Right? Data science was called the most sexiest job of the 21st century. Apparently there will be a need for more than 1 billion data scientists by 2018. There are constantly more jobs, more projects, and it's an active research area. Now, however, the reality of data science can often look like this. And so why is he so frustrated? Oh, he has to deal with raw data. And raw data is gnarly. And it can look like this, where you don't have nicely, even like not a structured data source like a database or a data warehouse, you have a text file. It's not a nice text file like a CSV where you know the delimiters, it's just some arcane delimiters that you need to parse apart. There might be errors in the data. You've got to reconstruct what things mean. And this is actually a file that looks fairly nice. This one doesn't look as nice because it's hierarchical. This is also actually like anonymized data that we've seen at customers. It's hierarchical data. So they've got a hierarchical text file that goes on and on and on and on with those cases. And the hierarchical structure is based on the position of where things show up in this text file. And now, well, it can be fun to analyze it and to parse it apart. I'm sure you can do amazing things with it, but it's not easy. And then there are obviously web data sources that report results in JSON or XML, where you also get lots of information that you need to parse out into rows into a more tabular format that can be used for machine learning or for further analysis. And that means that data preparation takes time. Actually, it takes a lot of time. So this is a citation from a study that one of our founders did. And the data analyst in the study said, I spent more than half of my time integrating, cleansing, transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis. This is not what the job is supposed to be. He's not supposed to be a data janitor. He's supposed to be a data scientist. And based on this, there was a New York Times article that framed this number again, like based on interviews with data scientists a bit closer, and they say data scientists spend about 50 to 80% of their time preparing unruly digital data. Now, this might not be true in every case, because you might have very structured sources like databases, but as soon as you go into a more unstructured space or get data from third-party data sources or even the internet that you can't really trust, then things get a lot harder. Now, one of the results is that data is wasted. So we're wasting data. We have a lot of data. We're wasting most of it. Forrester said that organizations, on average, they use only 40% of their structure. So this is data that's really nice and structured in warehouses and so forth for their decision making. And of course, it's worse for semi-structured, non-structured data, then it's around 30%. So we're wasting a lot of data. Imagine what you could do with that. And on top of those things, data is dirty. Right? So DJ Patel, I'm sure you all have heard of him. He said when he was talking at a CTO summit in San Francisco last year, every single company I've worked at and talked to has the same problem, without a single exception so far: poor data quality. There's incomplete data, missing data, duplicative data. If you try to build crazy things like machine learning, it's going to fail on you. Get the pipelines and other stuff correct, then build on top of that. And what he alludes to is the problem that also came up in the first keynote today is, if your data is bad, your outcomes might be bad, right? If you have missing data or biased data, well, then the outcomes will be biased. And they might not work in certain cases. So imagine, like, and this can be simple mistakes. Say you get your data, Facebook network data, you do the API calls, you forget that there's a limit of 5,000 in there. So you only get the first 5,000 results per person or whatever. And then you've got a chunk of data that's missing. This will completely bias every model that you build on that, like a friendship recommender or something. So it's really important to be mindful that data quality issues, they can have an impact on the end results. And even if they're in the end results, you might not know that that is the case, because it's really, really hard to recognize. So the reality of data science is really that 50 to 80% of the time is spent on preparation. that less than 40% of the data is being used, and that poor data quality can affect outcomes. So let's take a closer look at the actual activities that are involved in preparation and what the preparation process is. And then I'll go into tools and show you user interfaces and what we could do in this area. So data preparation activities. Well, there's discovery. Discovery can mean several things. It means finding data sets that you want to use. Right? You might have your one data set that you start your analysis with, but then there might be more data sets that you want to use to bring this data in. So which data sets would you use for that? What's the content of a data set? Really understanding what are the columns, what do they mean, what are the types, the semantics, the structure, patterns that are in there, trends. Do you really know what's in the data set until you open it and get a closer look? So this is what I mean by discovery. And finally, also identifying potential quality issues. When you've got this first picture, usually you start structuring things, especially if you deal with raw data like I've shown you before. So that again means like you look at the data, you try to identify the limiters, you try to break it into a more tabular format, into columns. Maybe you can extract structured information from semi-structured text. You can convert rows to columns and vice versa. You can extract values from nested JSON, from nested XML. And finally, you can aggregate and roll things up. So this is all changing the structure of the data. The data was always there, it's just you change how it's structured. Then there's the obvious one, cleaning. So cleaning, again, various things. Once you've identified the quality issues, there are things like converting different units to standardize, to normalize, fixing typos and names, like customer databases have the same customer several times, figuring out if there's invalid or missing data. Potentially it's irrelevant to your analysis. You can remove some rows that have missing values in some fields. But you could also potentially impute the data, so just do interpolation and fill it in, so there might be ways to repair it. How do you deal with outliers? It's also one of the things that falls in here. Does your outlier distort your analysis? Can you remove it? Is it irrelevant? Is it an error? And removing information that's not even relevant to the current analysis that you have in mind. And this is actually one of the really interesting steps to me. It's enriching data. So you start with your one data source. And usually the insights that you get from a single data source are, well, they're not that much. You're done with it pretty quickly. But the interesting and creative part comes when you mix together several data sources. Because first of all, there are like many combinations, and some of them make sense and others might not. But also you create value from two data sets that wasn't in the individual data sets alone. So this means joining things. It can mean like, well, standardizing different data sets like in that nation builder use case with the US states that I've mentioned, and then bringing them together via concatenation. It can also mean deriving new values using formulas, like in regular derive operations, in window operations over time windows and so forth, where essentially the new information is in the formula and then applied to the data. And once you're done with all of that, you want to make sure that, hey, are there any errors in there that can affect my machine learning? Are there any errors in there that can affect my further analysis, my dashboards, my KPIs? And the result of that is that the data preparation process isn't a nice waterfall flow. It's fairly convoluted, and it's a back and forth iterative process. So this is from one paper, again from our founders, who had a journal paper on data wrangling, and this is where he plotted some trajectories that he had observed in actual data scientists. So they start out with raw data, and you load it into your tool, you diagnose what's in there, and then you start transforming it, but you realize there's some problems. So you go back, you might structure it a bit more, clean it a bit more. See, now it's kind of good. This is, you can see the mouse, then you go out of your preparation phase, you load it into your visualization tool, and pretty quickly you realize, hey, this doesn't look right. There might be a null island, if you've ever heard of that. Like this, you have null, and it plots an island on your map. There might be some errors that you recognize in your visualization tool, very common. So you have to go back, clean those out. Then at some point it might look good, but you get an idea. Hey, I could use an additional data set to get a much more meaningful analysis with more value. So you go the whole way back, you bring that additional data set in. You're going through the same steps again. You transform it, you clean it, structure it, you bring it together with the first data set. And you go into your analysis. Now it's kind of like, You're here, it looks fairly good, a bit more, and you're done. But then, as you put it into production, at some point you realize that, well, my source data might be shifting, so newer versions, there might be certain changes, it's not quite the same anymore. So even in an operationalized environment, you might go through some data preparation steps again to make sure that newer versions of data sources that you're using are actually like matching your expectations. All right, so a very complex process. And how do we support this process? What are the user interfaces that we use to do this activity? Well, there's programming. I think this is the most common one. So you write a Python script, say, or where you do your data transformation, right? And it can take quite some time. Go in, you write the script, you run on the data or a sample of the data, you look at the results, you try to figure out what's going on there, you add a few operations, fine-tune it, and there are those long round trips. Similarly, and this is from many ETL tools, you have a visual data flow. It looks nicer, and at a high level it's really useful. The problem is it hides a lot of things that are, like, essentially the complexity is the same as programming, because as soon as you open one of those boxes, well, you need to specify the same things that you specified in text while you're programming. So it structures the problem a bit nicer, but it's really a superficial change. And finally, there's Excel too. So you can do this all in Excel. It's very direct. It does not scale. I mean, yeah. But people are actually doing this. So we need to rethink our UIs. Why do we need to rethink our UIs? Well, all those three cases that I've shown you are really UIs that were not developed with data preparation or with very agile data preparation in mind. Programming was invented to express computation, much more general problem. Data preparation is a much more domain-restricted problem. Then the ETL workflows were really aimed at people writing operationalized pipelines and not necessarily doing interactive data exploration and not for being agile. And finally, Excel is, well, a spreadsheet tool. Again, like a much broader use case than data wrangling. So when we're rethinking our UIs, I think it's very important that we try to, now that we're in the 21st century, we want to have UIs that, where the machine really does as much help as it can, but not more. And so human and machine work really in balance together. And what could this look like? So it's a loop, really. You've got the user, and then the user interacts with the tool, and the tool represents information in some sort and goes back to the user. But the important piece is to keep the strengths of each part in mind. So when you're the analyst, well, you know the goal of your analysis, you know the end goal that you have in mind. The machine can't know that. You've got a lot of contextual knowledge. This is all your world knowledge that machines so far don't have, but it's also all the knowledge in the organization. It's your context in the organization. So if you have a question, you can go to other people and ask them. So there's all of that, and that enables creativity and kind of like an idea of which data set to pick, an idea of kind of like who to talk to figure out what something really means. Right? You also have the power to make decisions. On the other hand, the tool can process a lot of data. It's just very fast at processing data and much more accurate. Right? And it also has access potentially to all the data transformations and data preparation that other people have done that you don't know about ever, right? in a certain tool space, right? So what does that mean? It means that a tool can do things like generating previews of what the results would look like. It can suggest your next steps because, well, it doesn't know exactly what next steps you would want to do, but it has a certain likelihood model. So it could say, well, 80% it's this kind of step, and it just shows it to you. And for you, the problem is much simpler because you get a list of like 5 things, say, and the chance that one of them is what you want is like 90%. And this can speed things up significantly. It can calculate distributions, statistics, some machine learning, automatically apply heuristics to identify data quality issues, and surface them in a really nice way that's aimed at our perceptual system, so we can perceive this information really, really quick, make our decisions really, really quick, or at least like explore certain variants. bring in all what we can do, and then we want to express the intent, on the other hand, to the tool. So assuming that you want to manipulate data, how would a tool know which data you would manipulate, want to manipulate it into what direction? So how can we express that intent that is in our heads to the machine, such that the machine can give us the best suggestions, show next steps, like really know what's going on, where we want to go and support us best. All right, so that's the high level idea. And a few concrete things that we've done with that in Trifacta are, for example, user interaction that drives smart suggestions. So what you can see here is a screenshot of our tool, a bit blurry. I'll show you a demo soon. But the idea is you interact directly with the data, you identify potential things that you might want to do, represent them in a visual way, give you a preview of what your result would look like, and then you can decide or refine, move forward really, really quickly. So essentially this loop from at the top left, where you select something with your mouse, say text, say something in a histogram, in a quality bar, we generate the suggestions, we show you a preview, and you can go through this loop really, really fast. And the nice thing about that is that working with data becomes a very direct activity that can be a lot of fun, actually. And so now for the demo. The demo that I've prepared is called Insider Fraud Detection. So you might remember that about 8 years ago there was all this financial scandal, and one of the problems that happens in finance is that there can be something called insider fraud, where say an analyst at a bank has access to privileged information. They're not allowed to use that information for their personal gain because it's not public yet. For example, a company, they might get a call and somebody might say, look, my company will give out a profit warning tomorrow. Right? Now if I know that a company gives out a profit warning tomorrow, I would short their stock, right? And make a good gain. See these are. So banks have a high incentive to crack down on that. Now how would you do that, right? How would you identify potential cases of insider fraud? And this is what this demo is about. Okay, I have to quickly adjust. Is that looking good? Okay, so the data sets that we have in this demo are two data sets actually. Like the power is to bring data sets together here. So one can, like the first one, the one that we're seeing here is a public news feed. So you could imagine a Bloomberg feed, where companies, when they post those news, they post them on a public news feed, and you could download this news feed from the internet. Right? It would look roughly like this. This is kind of like open data from the internet. So, this is the Trifacta user interface. So it shows you a sample of this data. So you can imagine this to be very large, and this would be the sample. For the demo, it's actually the full thing, but yeah. And what you see here in the interface is we do certain things automatically, so we split it up into columns as we recognize it. We identify data types as much as possible, and then we figure out if there are any mismatched values that don't fit the pattern for that data type, if there are empty rows with missing values, what the distribution is in a histogram. So for example, this is the data for news. And as I interact with, say, the mismatched data, then I'm not sure if you can see that. The green might not be that good on the monitor on this one. There you can see it, I think. So, so down here, this is light green. I'll actually put it in light red, maybe that's better. So this row doesn't match the format, and what I'll do now is I selected something else. I selected all the valid values, because really what I want to do is I only want to keep the news articles that are valid. So I select them. As you can see, we generate suggestions. One suggestion is previewed, and I can apply it, and then the data is removed. All the mismatched, all the empty data for the state news column is removed. Right? And this is the basic idea of this interaction model. And so now we can skim through and see that there are other columns, like a title column and the content column. And in the content, there are actually stock ticker symbols in there, but it's semi-structured and they're kind of hidden. So I'll start selecting the first one, and the blue comes through this. So, so you see I selected the first one and it suggests to replace it. I really want to extract it, so I select that. And you can scroll over and you see I would select this BBY. But really there are many more. So I give the second example. And it generalizes. So that's nice. I would now extract everything that's like uppercase and in those brackets in there. However, there's some cases, I'm skimming through, there's some cases where there are actually like multiple, right? So a news article could have references to multiple companies. And I want to extract all of them. So let's see if we have any other suggestions. We could extract it into a list. So this list now would give me all the stock ticker symbols that are in this news article. So that looks pretty good. I'll add that to the script. Now I've got this new column here, extract list, I could rename it, I'll do that later, that has those symbols. But assume that I have all the trades that the bank has made. Each trade is in a single stock. I want to join those two, I need a join key. So really I need to unroll this such that there's only, and I've clicked on the column again to like tell the tool, hey, I want to do something on the column, can you suggest me what to do? I want to roll this up, so I'm flattening it. And now, I'm not sure if you followed, but it essentially, if you have an array of multiple values, it now duplicates the whole row for each value in the array and just puts that value in there. So cancel this again. So you can see for the second row we have SSNLF and AAPL. I click on the column and I flatten it. And now SSNLF and AAPL are in their own rows, and the rest of the rows exactly the same. So we essentially duplicated those in order to prepare for later join. All right, and similarly, now in order to have real stock ticker symbols, we need to get rid of the surrounding delimiters. So I'll just select those. In this case, the suggestions look good. And I'll go quickly through that. It's essentially interacting directly with the data, which is the part that I personally really like. And then I can look at this information. Some news articles don't have any company names. So I'm selecting those and just deleting them because I won't be able to join them later anyways. All right, so far so good. We're almost done with this data set. The one thing that might be important later is to only focus on articles that have certain keywords. So there could be many. I'll focus on a specific one here, namely profit warning. And so I'm going to select this in the data. And again, I get suggestions. This time I could replace it. I could do various things. I just want to count how often it appears. So I just count how often profit warning appears. I get this new column. I see the distribution. There are a few cases where there are like 2 profit warnings, 6 cases where there's 1 profit warning, quite a few where there's nothing. All right, so I've extracted that. Now I'll do a quick few rename these. So this is the stock ticker. And this was the profit warning. And then I'll move into a new data set. All right, so switching to the other data set. So this is like the news data source. And as you've seen, like we've changed this quite a lot. We've changed the structure. We've done like a bit of cleaning. We've removed stuff that we didn't need. The other data set looks like this. Those are trades in the bank. Each row is a single trade. Okay? There's quite a bit of stuff in there that we don't need. So I'm opening a tool called Column Browser on the left. And again, I'm just saying I want to interact with various columns. And as I select multiple columns, the suggestion that I'm getting is to delete them. And this is a very typical step. It's just when you have a certain analysis in mind, get rid of or hide data that's not really relevant to it. So I end up with 4 columns. Right? And now I'm going to add new information by deriving values with formulas. So those are the trades per stock, and I'm really interested in trades that were abnormally high. Because if it's just a normal trade, then hey, this might be just coincidence that the trader has happened to trade something after a news article was published. But if the trade is especially high, it's kind of suspicious. So in order to figure out if something is an outlier trade, I'm going to derive, first of all, I'm going to derive the actual price of the trade. Right now we only have the price per share and the volume. So I'm going to multiply. And one of the nice things here is as you multiply, you get the new histograms. You can see, like, is the outcome correct? Are there any mismatched values? What's the type? It's all very interactive. And so now that I have this, I'll actually call it total. Now that I have this total, I can then go on and say, hey, what's the mean? What's the standard deviation? I'll just directly jump to the outlier here. Because you're all familiar with statistics, I assume. So let's say if the total is greater than the standard deviation of the total times 2 plus the mean of the total, then we have an outlier. That makes sense, right? It's 2 standard deviations away from the mean. We're only focusing on the large part, so if that is true, we have an outlier. We have this column here that tells me actually, like in this sample, there's 416 outliers. It is Boolean type. It all looks correct. And I'll call this is large trade. Oops. All right. So now I've got my is large trade column that I just calculated. This just shows you that it's often very helpful, especially if you make errors while you're typing in those formulas. It can be very helpful to immediately see on a bunch of example values what the outcome is. And you could even like do initial steps to just have the mean and so forth. And I made a mistake here. Somebody noticed the mistake? I guess not. I wanted to group this thing. I wanted to group it by the stock, because some stocks have larger trades as others regularly. Some stocks are just listed on small stock exchanges. There's not much trade volume going on. So I also want to group this by the ticker. And now I can at least see this has somewhat changed. And I've modified this transformation. All right. So this is a way where you can, if you recognize errors, you can correct them really, really quickly. Now it comes to bringing those 2 data sets together. And the other data set was the news data set, so I'll quickly preview that. And see, and select the join keys. So it recommends to join on the ticker automatically. I'll include everything here, and we can be fine with an inner join, because if a certain news article doesn't match the stock ticker, then we don't need it. So I'll join those together. Now I've got the joint data set, and now I'm going to reduce it to just show you how you can narrow it down. First step in reducing would be to figure out if the day trade is actually after the date of the news. Now, looking at it really quickly again, I'm just doing this initial profiling step. I see that there's something going on here. First of all, there are mismatched values. So I click on those to get an idea. Here they are. And also, the date of the news is on a minute level. The date of the trade is on a millisecond level. So I'm going to change this to be on a minute level also by just going in here and selecting what I want. And then I get a card let's replace this particular instance. So showing me this instance would be replaced. And there are actually like various other alternatives. So I could go in and match a certain pattern, remove all this, and make the date of the trade also to be on the minute level. As I can see in the histogram quality bar, the errors are now gone also. So I'm making sure both are on the same level. All right, and then I can say, hey, I want to just keep the rows where the date of the trade happened after the date of the news. What would that look like? Right, and I'm not sure, yeah, here you can see it also. The interesting piece is, even in the histograms and quality bars, you get now the distribution of what you've selected, what you would keep. So you can see that in a slightly darker shade of green. And you could, for example, see a pattern here that the more recent the trade is, the more likely it is after a news article. And in this case, it's because our news set was really limited. So and then the newer trade is, obviously there has been news before it, so it's getting more and more likely. So this might be an indication of something that you want to take a look at, that you immediately see because you profile the data while you're working with it. All right, I'll ignore this for now, but then you can see after I added this J trade, it looks kind of very increasing. All right, so I've done that. Now we only have rows where the trade has happened after the news. Next, I'll just focus on, again, by selecting the large trades, I'll just focus on the large trades. Now we only have the ones where we have large trades. And finally, I'm going to remove all trades that don't have a profit warning in them. And at this point, I'm down to 2 trades in my sample. Right? So just filtering down based on various criteria, and I could now go ahead and run a job at scale in my Hadoop cluster on like much larger data sets than I initially got a random sample or a top sample from. And then if there are further anomalies, I bring that back in and correct the data. In the interest of time, going back to the presentation now. And we'll talk a bit about the path forward for this, right? So now this is kind of like what we've developed over the last 3 years. But they're like in the data preparation space, there are more hard problems to solve, like schema matching, standardization, quality assessment, and so forth, combined with technical challenges, because many things that are true in a data warehouse or database scenario don't hold here. Because you're changing the data so quickly, like all the pre-computation you get in databases, like database indices and stuff like that, is of limited value because, well, if you need, it's essentially a trade where you move the index creation, which is really expensive, in the hope that that you read from the data very often and use those indices. But if it's only one-off, it doesn't make sense to create an index. So how can we deal with those things? How can we deal with performance at scale when there is no computation, but there is heavy string processing and dirtiness? Right? And how can we enable immediacy, like this really fast feedback loop for other parts where you might have standardization, but in order to make sure that the entities are correctly resolved, you could do that on the sample, but how does it scale up if your data set is several terabytes? How can you ensure that, right? How can we steer computations where we get results back quickly? What are the user interfaces that are optimal for situations like that, where people don't have to wait to be able to work with data? All right, so it's just a few high-level ideas. In order to sum up, the key thesis of this talk is that data preparation is an essential part of data science, and it can take up to 80% of the time. Productivity and data quality are the central challenges, and the human needs to be in the loop to get this in a very good state, because we have the creativity, we've got the decision-making abilities, and so forth. So it's important to design tools that leverage strengths of humans, strengths of machines, and have a closed loop where you can immediately work with data where it feels very, very direct. All right, with that, I want to thank you. Yeah.